All right, in Chapter 3, we're going to look at measures of central tendency, more commonly known as the mean, the median, and the mode. And these are three ways to describe where the center of our distribution is, or the center of our data. And there are the three different ways to do that. And they are ways that we can figure out what the average is, or what a typical score is, or most frequent score is, or most representative score is. And so there's three different ways to do this. The most common one, the mean, we'll deal with first, and then we'll look at two others when the mean is not practical. So before we get started, I want to kind of bring to light some notation problems we're going to have throughout this semester, and that is that behavioral statisticians use different types of notations because of the different types of samples we're dealing with than do necessarily mathematical statisticians or business statisticians and so forth. So if you go out onto your Google machine and look up videos of how to do these different things, number one, that's great. If you don't understand it one way, keep searching for more and more explanations until it clicks. However, be aware that the notation that people in these videos use may not look like the notation in your book, depending on the perspective that they're coming from. For example, real common difference between the psychological us and everybody else is that everybody else tends to use this X bar to represent the mean or the mathematical average to their information. However, we use different symbols. For example, for a sample mean, so the average of all the grades on test 1 for your class, you are a sample of all the stat students I've ever had. I'm going to use the letter M that you're used to, the American letter M, which is the same thing as X bar. However, if I were to take all of the students I've had so far, so my entire population of test 1 scores, and get the average for those, instead of using letters you're used to, we're going to use Greek letters to represent that. So in this case, the Greek letter mu, looks sort of like a curly Q, is going to be used to represent X bar in that case. It's just giving a little more detail to what we mean by arithmetic average. And so there are a number of symbols that for us in our book are going to be different than the symbols you'll see in other books or on YouTube videos or whatever. But as long as you pay attention to the terminology that's being used, you should be able to sort of equate that pretty well. But I just kind of want you to be aware of that when you use those other resources. And again, I do encourage you to go ahead and do that, but do that with the awareness that things might look a little different than they do in your book. And in fact, I even use some videos, because they're really good, that use some of this alternate symbology. So now you know to kind of pay attention for that. So let's talk about the most common commonly used measure of central tendency, which is the mean, aka your arithmetic I cannot write average, nor can I spell, so that's just kind of how it goes. But that's why I teach math. But that's kind of what you're used to when you get your average score for your class. Then that your average is your mean, the kind of middle of all your performances for that class. All right, so let's look at our formulas. Two different formulas, even though they're exactly the same formula, their symbology just changes to reflect whether we're talking about a population of scores or a sample of scores that we're going to use probably later to represent or estimate a population. So population mean is represented by the Greek letter mu, All right, that we mentioned already, right there. And in order to get that, you're going to add up all of your x's. Now, we talked earlier that this symbol sigma merely means add them up, right? Sum of. It's an instruction, not an actual number. So sum of all of your x's. So all of the numbers, all the scores in that population, you're going to add them up, and that's what you're going to put on top. And then we've got the big letter N to represent the number of scores in our population. All right. So moving down, sample, process, same. This still means sum of. So you're going to add up all your x's. But in this case, you're going to have a sample of scores rather than all the possible scores. So we're going to represent that with the American letter M and a little n to represent a little part of the overall. All right, so just kind of keep those things in mind. In the end, when you're calculating, it is the same formula. It's really nothing's changed. It just tells you in the formula, and therefore when you report it, whether we're talking about a population or a sample, and that will explain to us exactly how far-reaching our data can be used. And so here's a quick example of how to do that. It does use some of that alternate terminology that we talked about. It uses X bar to represent the mean. In this case, since there's only 9 data points, I'm going to guess we're probably talking about a sample. So X bar instead of the capital letter M. And then instead of just saying sigma X, they use sigma XI. XI is just another way of indicating we're going to add up all the X's. And so XI represents X1, X2, X3, so our whole list of X's. And then our N is the same. And so here's just a quick example. You probably already know how to do this, but how to calculate your arithmetic mean.
Welcome to My Secret Math Tutor. We're going to run through a real quick example on how to find the mean. So to find the mean, we need to use this formula right here. Now it looks a bit confusing, but don't worry, here's how we can translate it. This X bar on the end represents the mean, as long as we're dealing with a sample from a population. Over here I have sigma xi. That means they want us to add up all of our data points. And it's divided by n. What's n? Well, n is how many of those data points we have. Okay? So let's take our data and see how this formula works. So the top part, it says add up all of my data points. So I take 4, 4, 5, 7, 8, 9, 10, 12, and 15. I basically add all of those guys up. Then I would divide by how many of them I have. It looks like I have a total of 9. Now you may have to use a calculator if you have lots of different data points, but that's okay. When I added everything up, I got a total of 74 divided by 9. Now oftentimes, it's good to take this all the way out to a decimal. I got 0.91358. And there you go. This represents the mean for our data. If you'd like to see some more videos, please visit mysecretmathtutor.com.
All right, so that gives you another place to look up some of these cool little videos as well. So there you go. Arithmetic average, probably something you've been doing since 4th or 5th grade. So simple enough. Now, it can get a little more complicated, particularly when you're trying to figure out what your final average for a class is going to be, because that is usually a weighted mean. In other words, some assignments count more than others. So an example for that might be, and I'm just going to use a generic, this is not pertaining to this class per se, but in a given class, your homework may be worth 10% of your grade. And your, let's say you have papers to write. And those papers would be worth, say, 30% of your grade. And then you have some tests. And those might be worth, let's say, 20% of your grade. Then you have a project worth 10% of your grade. Where am I so far? 50, 60, 70. And so a final, maybe worth 30% of your grade. Okay, great. So we have all of our scores for all of that. Let's say our homework, so there was 5 homeworks. We got 100, 100, 90, 100, 85, and 100. Cool. And then papers, let's say we had 2, and we got a 90 and a 80, because papers are harder to get 100 on. Tests, let's say there were 3, you got a 100, a 90, and by the end of the semester you were just done it, so you got a 70. And then your project, you went, oh crap, and you got it together, so you got a 100. And on your final, you pretty well had it together, so you made a 90. Great. Now, if we were just doing a straight arithmetical average, what we would do is add all of those scores up and divide by however many there are. What do we say? There were 6, 7, 8, 9, 10, 11, 12, 13. So divide by 13. But that's giving each one of those scores equal weight. And that's not how your grade's to be calculated. So instead, we have to calculate basically an average for each of these columns and then use that average in this representative way. So how you do on your papers in your final are going to change your score more than how you do on your homework or your project, which are worth less. So that's what a weighted mean is. So let's take a quick look at an example of how to calculate that.
This time, we'll demonstrate the calculation of the weighted mean. We'll start with 2 samples. The first sample has 4 scores and a mean of 8. The second sample has 8 scores and a mean of 5. The problem is to find the mean if the 2 samples are combined. Now, to find the mean of the combined sample, we'll need 2 things. We'll need to know how many scores are in the sample, and we'll need to know the sum of the scores, and those 2 values are necessary to calculate the mean. The number of scores is easy. We had 4 scores in the first group, 8 scores in the second, so there are 4 plus 8, a total of 12 scores in the combined sample. We'll use that same process to find the sum of the scores. The first sample has 4 scores with a mean of 8. By one definition, the mean is the amount that each individual gets if the total is distributed equally. For each of 4 people to end up with 8, the total has to be 32. Second sample has 8 people with a mean of 5. Again, that's 8 people, each get 5, for example, $5. Each of 8 people gets $5. The total has to be 40. For the combined sample, we have 32 points in the first one, 40 points in the second. 32 plus 40 is 72. The mean then for the combined sample is the sum of scores, 72, divided by the number of scores, 12. 72 divided by 12 is 6. The weighted mean is 6. Now notice that the weighted mean is not halfway between the 2 means. It's much closer to 5 than it is to 8. That's because the mean of 5 is from the larger sample, and the larger sample carries more weight in determining the mean.
Okay, so there you go. Now you know how those weighted scores work the way they do. Another sort of handy tidbit for everyday life. And when you're looking at your scores in Canvas, the upside is it automatically weights those things for us, so you can kind of see when you look at your grades what percentage each of those items is going to be worth in your final score, and therefore just intuitively which ones are going to matter more that you do better on. than others if you have to make sacrifices. But it also explains why, just because you did all your homework, say in this case, that 10, you did all of that, but you failed to turn in paper, that's going to cost you more because the papers are worth more. So that's another idea. All right. So another thing that we need to do frequently is figure out the mean from a data presented in a frequency table. And so to do this, the process is the same, but what we have to always remember is to get our total of x, we can't just add up the x column by itself. That just tells me what scores are available. Remember, my frequency column tells me how many people got that score. So just sort of like the weighted mean, it gives me how much that score is represented. So I have to first multiply f times x and then add that up to get my total of x, which in this case is 66, right? Because it represents each score that was in my data set. 10 was only there once, so that's fine. But 9 was in there twice, so I had to use it twice. And 8 was in there 4 times, so I had to use it 4 times. And so always remember to do that part first. You can even write the formula out to represent that. You could say that the mean, in this case, is the total of x times x over the total frequencies, which is one of the ways to calculate n, right? N is the value we get when we add up all the number of times scores occurred, because there's one score for each person. So in this case, 8. So here's another quick example of how to do that.
Hi there, welcome to a statistics video which explores how to find the mean from a table, from a frequency distribution table. I know we can find the mean by adding up the scores and dividing by how many there are if you've got a small amount of scores. And we can also find the mean on the calculator, but this is how to find the mean from a frequency distribution table. So here's a bunch of numbers, and we can put them into a frequency distribution table where we have the scores, and we can tally up how many of those scores we have, how many times each of those scores occur, what are the frequencies of each of those scores. So we did this in a previous video about frequency distribution tables, so we'll use that same data to illustrate how to find the mean from this situation. So what we do is we add an extra column we call the fx column. Now we call the scores the x column, and the frequencies we call that f, the f column. And fx in algebra, when things are beside each other, letters are beside each other, there's an invisible multiplier. We consider them to be multiplying together. So that fx column, all we do to find the number that we need to put in there is to multiply the score by how many times it occurs. So what that does is it really adds up the totals of the scores, because if you've got 3 scores of 2, then that's adding 6 to the total. And 3 scores of 7 is adding 21 to the total, etc. So that's really our total column, this fx column. And the f column is really the number of scores we have. So in the end, what we're doing is finding the total of the scores and dividing by how many there are. And so that's how you find a mean generally. You add up the scores and divide by how many there are. So let's fill in this frequency times score, or fx column here. All it is 2 times 3 is 6, 3 times 7 is 21, 4 times 2 is 8, and all we're doing is multiplying the score each time by how many times it occurs. 6 scores of 5 in this case is 30, and 5 scores of 6 adds 30 also to the total, and 2 scores of 7 adds 14 to the total. So we've got the fx column filled in there. We'll just get some totals here. The sum of the frequency column is important for us, and the sum of the fx column is important for us. So we'll add those two up. If we add up the frequency column here, we'll have 25 as the total. There are 25 scores. We could double check. And the f times x column, we add those numbers together and we get 109. So how we find the mean is we take the fx column and divide by the f column. So this is the arrangement for finding the mean from a table. We create an fx column and add that up, and put the sum of the fx column over the sum of the f column. So in this case, the sum of the fx column was 109. Put that on the top. We'll divide by the 25 scores we have. So it's the total still divided by how many there are, and that gives us a mean of 4.36. And there we have it. So we create an extra column from a normal, add an extra column to a normal frequency distribution table, and we get the totals of those two columns, the f and the fx column, and we put in that arrangement, big number divided by small number in this case. So that's how we do it. Sum of the fx column over the sum of the f column. Now I wanted to alert you to the fact that some textbooks have a funny symbol, mathematical symbol for the phrase sum of, and that's a funny looking E symbol. And so it's that symbol of the fx, so the sum of the fx column over the sum of the f column. So if you see that in a textbook, that arrangement there, then don't be put off by that. All that symbol means is the sum of. So those two boxes are really saying the same thing.
All right, so there you go. And it even made reference to some of our notation differences. All right, so let's look at some of the characteristics of the mean. So you don't necessarily have to recalculate your mean every time something happens. And so now we're going to look at, okay, what situations would we have to do that and which wouldn't we? First off, if you change a score in a set of scores, then your mean will almost always change. Really can't think of a situation that would. So in changing a score, we're pretty well going to have to recalculate our mean and figure it out again. So for example, if we have a score set of 1, 2, and 3, all right? And we add that up to calculate our mean, all right? 1 plus 2 plus 3 is 6, and we have 3 scores over 3, so the mean is going to be 2. If we were to change one of those scores, say the 2, let's say we change it to a 5. Now, we still have 3 scores, so I'm still dividing by 3, but now my sigma x, my total of x, is bigger. It's now 9 because I have that bigger score, which means my average is going to change as well. It's now going to be 3. So pretty much whenever you change a score, you're going to have to recalculate and work it up a little differently. All right. Now, if we add a score to our list of scores or we remove a score from our list of scores, again, it's pretty much always going to change the mean. There's only one exception to this, and that's when the score that we add or the score that we remove was in fact equal to the mean. That's just taking one of the ones out of the middle, and so the overall is not going to change in that case. But other than that, when we add or remove our score, it will always be the same. So let's take again our original example here of 1, 2, 3. Boop, boop, boop. That's our original set. And now I'm going to add a score. I got, a student took their test late. So now I've got a 1, 2, a 3, and the late student got a 6. Maybe they cheated. I don't know. But anyway, that means that both my top and my bottom number are going to change. My total of x now, including the 6, is 12. And my n now, including the 6, is 4 instead of 3, because I got one more person. And so 12 divided by 4 is 3. So my mean is changed by adding that score of 6. In this case, it went up. Let's say, however, that same set of scores, 1, 2, and 3, but 2 drops out of the class. Hate to see him go, but everybody's got stuff they got to do. Now, my mean was originally 2. Well, look what happens. 1 plus 3 is 4. Now I only have 2 scores to divide by, which is 2. So 2. It didn't change because my relative data didn't change. So that is, how that kind of works. So if you introduce or remove a score, any score other than the mean itself, then that will change your overall result. Now, if we add or subtract a constant to each score, that means I do the same thing for each score. Like, for example, y'all frequently call this curving a grade. Don't call it that anymore. And in a later chapter, when we start talking about the normal curve, we'll explain what that actually means. But when you say that, what you're usually asking is, will I add points to everybody's score to account for some error, some problem, something, and make everybody's score look and feel better? And not an unreasonable question, just use the right terminology to ask for that. Because what that does is whatever I do to every score in my distribution, it's going to do the same thing for my mean. So I don't necessarily need to recalculate the whole thing all over again. I just have to do to the mean that existed to begin with the same thing that I did to each score. So, for example, and I would never do this, but let's say I was, I don't know, having a moment and just feeling a little jerky, I don't know. And I'd say, you know what, I'm going to take a point off of each of you because, I don't know, I'm just in a bad mood. So instead of 1, 2, 3, my scores are now 0, 1, and 2. I said, I will never do that to you. That's just mean beyond words. All right, but that means my new mean is going to be a total of 3 divided by 3, which is 1. All right, remember that my original mean was 2. I subtracted 1 from each score. If I subtract 1 from my original mean, I get 1. Same thing. So instead of having to add to each of our data points and then recalculate, you can just do that addition or subtraction to the mean. Same thing goes for multiplication and division. Whatever I do to each score, I can do to each mean. So, for example, if I took my 1, 2, and 3, and I decided I was going to multiply it by 2, x times 2. All right, so it's going to be 2 times 2 is 4, 2 times 3 is 6. All right, when I add those up, it's going to give me 12. Oh, pen's working funny. 12 divided by 3, which is 4, which if I took my original mean, which was 2, and I multiplied it by 2, just like I just did each score, I get 4. All right, so that's how we can sort of manipulate or anticipate what's going to happen to our mean based on changes to scores within our data set. All right, so that's it. That's a big picture of mean. The next two, median and mode, are slightly more simplistic, but sometimes they're a better representation of our overall data set, particularly when there are, certain circumstances. So the median, essentially, it's just the score in the middle. So if I have 1, 2, 3, 4, 5 scores, all right, so x 1, 2, 3, 4, 5, I mean, one in the middle. If I have an even number of scores, then it is going to be a weighted combination of the ones that fall in the middle. And depending on how many there are in the middle, it's going to change exactly where that's going to fall. But frequently we're just looking for, what's halfway in between. So, all right, so we're going to look at the two most common situations for finding the median or the middle score in a set of scores.
Welcome to My Secret Math Tutor. In this video, we're going to go over 2 examples on how to find the median. Now, what the median is it's basically the middle of our data. All right? Now, 2 situations may occur, and that's why I have 2 examples. All right, so let's go through the first one. You'll notice that I've organized my data from lowest to highest. This will make identifying the middle much easier. All right? So we're going to move in from the lowest value and the highest value until we eventually reach that middle. So the 14 is our median. All right? Now you can see that if you have an odd number of values, there will be only one number for the median. In the next example, I have an even number of values, and watch how this process works out. So again, I start from the lowest number and the highest number, and I work my way to the middle. Now this time, there is no number in the middle. Well, what I can do is instead take the average of these 2 numbers, the 46 and the 48. So basically add them together and then divide by 2. This is how we will get a new number, and this one we will call the median. And that's all there is to it. If you'd like to see some more videos, please visit mysecretmathtutor.com.
Okay, so why would you want me to use a median to describe a set of scores instead of a mean? Well, let's say I have 3 students, and on test 1, 2 students make a 90, and 1 just doesn't even bother to show up. Well, if I want to say, how did my class do? Well, if I just take an arithmetic mean, then I'm going to take my total of all my scores, which is 180, divided by 3, which is going to give me an average of 60. But 60 doesn't really represent how well my students did, because it's letting that one student who didn't show up pretty much drag everybody else down with them. So instead, I might want to list these lowest to highest and say that middle number really is a better representation of what my students overall are capable of. So there's one example of when we might want to use median instead of a mean. All right, the last one is the mode. And the mode is simply, it's the most frequently occurring score. It's the thing that happens the most. And this is really great, particularly when either we have a really, really skewed distribution, or we're using things that aren't quantifiable. Okay, so for example, let's use the test 1 thing again. All right, so I got 1 person that didn't take it, 1 person that probably shouldn't have bothered, a whole bunch of folks who, did pretty darn well, and then, the ones everybody loves to hate. And so I could average that all together, or I could just take a quick look at that data set and say, you know what? This score occurred way more than everything else. And so therefore, that's a pretty good eyeball estimate without having to do any math of what my students in general know. Another thing is when we don't have anything, when we're doing something that's not quantifiable, so not numerical. So in other words, your favorite movie. Let's say our options are, I don't know, Harry Potter. Let's go with the first one, because, the first one's always the best one. Let's go with, this is Spinal Tap. If you want great bad 80s movie, that's a good one. Let's go with, I really don't know any good romantic movies. Let's go with fun. How about Despicable Me? That was cute, right? Minions and all that. And so, let's say that in our sample, 100 people thought Harry Potter was awesome, and that only 3 of you even knew what This Is Spinal Tap, that it was a movie at all, and that 97 of you liked Despicable Me. So real quickly, we can kind of look and say, all right, in this case, Harry Potter wins because the most people chose that. We can't really, create an average of those 3. What is the average of Harry Potter, This Is Spinal Tap, and Despicable Me? I don't know. Star Wars? I don't know. Right? It can't be done. So this would be a reason to use the mode. So let's take a quick look at that in action.
In this video, we want to find the mode for a set of data. If you've never heard of the mode before, let's take a quick look at what that means. The mode is the value that appears the most often in our data. Now, sometimes when you're looking at data, there may not actually be a value that shows up the most number of times. Maybe everything only shows up once. For data like that, it does not have a mode. There are other types of data where you may end up with a couple of values that have exactly the same frequency, so they show up the same number of times. And in situations like that, we call it bimodal. In a nutshell, though, you're just really looking for the values that show up the most often. So with that idea in mind, let's take a look at a couple of sets of data and see if we can find the mode. And looking at the first set of data, we can see that 0 shows up 3 times, 1 shows up once, 3 shows up once, and 2 shows up 4 times. So 2 is the most often, so I will say my mode is 2. All right, real quick, let's try this again. Another set of data here, I can see that 1 shows up 3 times, 2 shows up once, 3 shows up once, 4 shows up twice, 5 shows up 3 times. So it looks like 1 and 5 both show up the most number of times. So I'm going to say my mode is 1 and 5.
All right, so there you go. Easier ways to do this, of course, would be to go ahead and create your frequency table and just find the one that has the biggest number, or draw a histogram or a bar graph and find the one with the tallest bar. All right, so that's ways to do that, ways to find it. Now, each of these 3 types of central tendency can also be used to figure out what the shape of our distribution is, even just knowing those 3 numbers. So in a perfectly symmetrical normal distribution, all right, and we need to write that word normal on here because there are other symmetrical distributions that are not normal that don't fit this, and we'll hit those in just a second. But in a perfectly symmetrical normal distribution, the mean, the median, and the mode will all be the same. Now, that doesn't necessarily mean that that's true for every symmetrical. Some symmetricals will only have a mean and median that are the same, and the mode may not be. So kind of keep that in mind. And then on either end of your scale, if you have a positively skewed, in other words, more of the numbers are going to be stacked up on the left side over here. All right, remember your mode is your most. So if you stack your mode on the left side, then it's going to fall off to the right. Remember that it's pointing towards the positive, so that's a positive skew. Likewise, if your mode ends up far to the right, that means it's going to fall to the left, and that's going to get you your negative skew. So just by knowing what these numbers are relative to each other, we can then kind of sketch out what our distribution is going to look like there. And so here you go, another picture of that stack up, positive and negative. And now I said that sometimes all three are not going to be the same. So here's our normal distribution. Mean, median, and mode, all the same. But the second one is what we call a bimodal. There are two. So in which case, it's still going to be symmetrical. One mode here, one mode here, and the mean and median are going to be equal. Now, if we have a bimodal not symmetrical distribution, let's say we have stuff really high here and then not much in the center and then here and then some more over here, then you know, we're not going to be able to use that order of distribution to figure things out. So this has to be when it is symmetrical again. And again, we could have mean and median be the same in a non-modal type distribution. All right, so but all of these require that it be symmetrical in order for that whole, you know, here's what my graph is going to look like bit to work. All right, so let's look at when each of these measures of central tendency might be useful. One example would be, and you can chew on this for a second, my husband and I together have currently, at this recording, 14 cats and 3 dogs. It was not intentional, just sort of worked out that way. We've also rehomed well over 20 cats, kittens and cats, mostly kittens, and 5 or 6 dogs as well. If you come to my house, you will find that the messages all around my house to every animal on the planet is come to the Allen's house and they will take care of you. So somehow we got to this. So by using mean, median, and mode, we can kind of determine exactly how unusual my husband and I are.
I'm staring at my cat in the window right now and wondering how many cats on average do people own? What is the national average for cats owned by people? Measures of central tendency is a set of descriptive measures which indicate the typical score. When conducting research, we need or want to know what is most likely going to happen. To say it differently, we sometimes want to know what has the highest probability of occurring. A researcher seeking funding may want to know about a psychological service center's most common diagnosis and what are the problems most likely faced by the client. If the researcher knows the center deals mostly with smoking and drug addiction, then they most likely would apply for money to help with those services. The 3 main types of measures of central tendency are mean, defined as the data's average score of the sample, median, defined as the middle score after the scores have been arranged in numerical order, and mode, defined as the most often occurring value. When trying to understand how typical or normal data is, we, as researchers, need to differentiate and know the difference between a population and a sample. A population is defined as the complete collection to be studied. So if you're interested in mental health of your city, a population data set would be all of the people in your city. A sample is defined as a section or part of the population, and would be anywhere from 1% to 99% of the city's population. Mean, or average, is simply all of the scores added up and then divided by the number of scores. This will give you a score that, if you were to graph it, would be somewhere in the middle of all of them. Mean is useful for understanding what score is most likely to happen. When other statistical tests fail and you can't use them, you rely on the mean. Means in relation to samples and population have to do with accuracy as well as relation. Accuracy has to deal with the sample being representative of the population. Because most researchers work with samples, there is an attempt to have a mean match up closely with the population that you're interested in. To use my cat example, if the national average of cats per household is 1, and we took a sample of all my friends and found that the average number of cats between us was 3, That means I have a lot of cat friends. Averages and individuals also have a relationship. If the national average is 1, and my friends have an average of 3, and I have 4 cats, that tells us that I have more cats than both the national average and the average of my friends. Sometimes when collecting information, a researcher will have a group of data that is way off to the side. This is known as an outlier, or a point of data that is distant from the others, either extremely high or extremely low. When you plug it into the mean, it will skew your results. Like if you had someone in your study with 86 cats. They're going to really throw off your results. Because this one person can throw off your results, the next best way to describe your data is median. Medians are useful for understanding what the central part of the data looks like. If there are a lot of lows and highs, then this score will be least affected by it because all you do is count to the centralmost number where the scores are in numerical order. If there are 2 central numbers, you simply average the 2. Medians don't have a direct relationship to the sample and mean, because individual scores can vary. Similar to the mean, you want to get your sample as close as you can to the population. The issue with this is that many articles may not report a median because it's so easily pushed one way or the other. Mode is the most often occurring number. This is likely never going to be reported unless you're looking at a very specific piece of literature. For example, the study on cats may report that the mode is 0. This means that most people don't have a cat. Mode can also be 2 or more numbers occurring at the same frequency. So if people are just as likely to have 2 or 0 cats, then you report 2 and 0. This makes mode highly subjective to your sampling technique. If you go to a place where people have a lot of cats, then your mode will likely be much higher than the populations. If you go to a place where no one owns cats, then your mode will also reflect this. Mode likely has the weakest link to population due to its sampling bias. It can be reported to give the reader of your research an understanding of what the average score looked like. This may be important if your mode was different than the average. If your mode was 4 cats and your average was 1 cat, that means something very strange is happening. Measures of central tendency is a set of descriptive measures which indicate the typical score. They can be affected by an outlier or a point of data that is distant from the others, either extremely high or extremely low. The 3 most common measures are mean, defined as the sample's average score, median, defined as the middle score after the scores have been arranged in numerical order, and mode, defined as the most often occurring value.
All right, so that's a pretty good sort of summary of how we choose and why we use each one of these. Just real quick, kind of run you through that one more time. Using the mean, whenever we can create an arithmetical average, that's what we're going to do. Median, all right, when our average isn't going to be very representative. For example, when the scores are extreme or skewed, remember I gave you that idea, we got 1 0 and 2 90s or 4 90s for a test, then yeah, the average isn't going to be as representative. If we have scores that we don't know yet, say 2 people haven't taken a test, then I might use my median to give me an idea of how I expect them to do. When there is no end to how well or how poorly you can do, or again, if it's an ordinal, first place, second place, third place, that sort of thing. And then mode, we talked about it being those nominal or name scales like the movies. If, we only have like absolute categories, or when we want to try to describe a shape, where our mode is located will help us